The Doppler effect explains how things sound different if there's motion between the source of sound waves and the observer. If we think about a tuning fork just sitting still and sending out sound waves, if we could see the air, there'd be ripples of high pressure coming off both sides of the tuning fork. Pretend these lines represent the wave crests. We can't see sound waves, but imagine those are the high pressure waves. They'd be coming off both sides of the tuning fork, going both directions. If I take my time and draw that better, those waves should all be evenly spaced. If your ear, if you're the observer, was over here, as those high pressure waves got to the observer, they would push the eardrum in a little bit. In between the high pressures, the low pressures would pull the eardrum out a little bit, and the listener would hear the note that the tuning fork was playing. Similarly, behind the tuning fork, the observer back here would hear the same note, based on the frequency of the eardrum being pushed in and out. If we have an identical tuning fork, but it happens to be moving, let's say this one's moving to the right a little bit, we'll say that the object is moving. If the tuning fork is moving, the impact it has is that it squishes the wave fronts in front of it together a little bit more. If I could draw that perfectly, the spacing on these would be a little bit closer together on the side in the direction that the tuning fork is moving. Similarly, the wave fronts behind the tuning fork would be spread out a little bit more by nature of the motion. What this means to your observers, if you're standing in front of the tuning fork, or as the tuning fork approaches you, since those wave fronts are squished together a little bit more, they're going to hear to your eardrum a little bit more closer together in time, or with a slightly higher frequency. The frequency you hear as the tuning fork approaches you is a little bit higher than it was when it wasn't moving. Standing behind the tuning fork, or if the tuning fork's getting farther away from you, the frequency that you hear is going to be a little bit lower. Since the spacing of those wave fronts is spread out a little bit more, you hear them a little bit less often, or a lower frequency. Since there's two Doppler effect, there's two versions of the equation. If the distance between the source and the observer is getting smaller, you hear a higher frequency. In the equation, use the version with a negative. If the distance between the observer and the source is getting larger, maybe the tuning fork's moving away from you or you're moving away from the tuning fork, if the distance is getting larger, then use the version of the equation with a plus. Then it's just a matter of crunching out depending on what you're given. Let's try this example. Tuning fork ringing at 512, so that's the frequency. It's moving towards you in 15 degrees Celsius air. In this subject, whenever we get a temperature, really that's telling us the speed of sound. Every degree Celsius warmer, the speed of sound goes up by 0.6. So for 15 degrees Celsius, the speed of sound is 341. Since it's moving towards you, that means the distance between you and the tuning fork is getting smaller. That means we're going to use the version of the equation that has the negative sign. It will look like that. I'm out of room, so I'm going to flip screens so we can crunch this one out. So next screen, the speed of the object was 10 meters per second. So we can go back to F prime. That's what I'm going to use for the new frequency, or sometimes I call it the perceived frequency. It's the old frequency. For this question, it was 512. Multiplied by the speed of sound. For this question, it was 341. And since it's approaching, it's a difference. 341 minus the speed of the object. If we crunch in on the denominator, it's 341 minus 10. If you do that math on that, moving 10 meters per second makes that tuning fork sound like it's 527 hertz. That's a number that's a little bit larger, a little bit higher pitch than 512, as expected. Since it's moving towards the observer, we should hear a higher pitch.